Math wasn't made to harass English mages. It was invented by a little something called nature. And it's everywhere you look. In fact, there are specific numbers that we see in nature all the time. Together, they're called the Fibonacci sequence. And it goes something like this: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on. You may know this pattern. The first and second add up to the third. The second and the third add up to the fourth. The fourth and the fifth add up to the sixth, and so on. You can draw one for yourself like this. The sequence was first described by mathematicians in India about 1,300 years ago. Fibonacci was a mathematician, and in his book 𝑬𝑵𝑵 he described the sequence with a thought experiment about calculating the growth of rabbit populations. The number of pairs of rabbit in the nth month is the nth Fibonacci number. But the easiest place to find these numbers in nature isn't in bunnies. It's in plants. Your job as a plant is to deal with your seeds and leaves and petals. You're gonna grow some seeds. This is not how flowers actually grow, but there are connections. This is the center. When you grow a seed, I'm gonna represent that by putting a little blob. Now that's a seed you've grown from the center of your flower. And one option you could have is you've got to decide where to put your seeds. And I'm going to give you the option of only how much do you turn around before you grow your next seed. So you put a seed down and you can turn a bit. And put another seed down, so I'm going to talk about fractions of turns. This is a fraction of a turn of 0. If you turn half a turn, it just makes 2 lines. So if I jumped, say, to a tenth of a turn, would you care to predict what you would see? That's right, 10 spokes. Let's try 2/5. That is 0.4. So as predicted, we have 5 spokes here. What's interesting is if you change this number very, very slowly, and you realize that a tiny change gives you very different behavior. So this number is changing ridiculously slowly. But even a small jump is giving us spirally shapes. And very quickly they stop looking like spokes. For any rational fraction, eventually the star will close. But what if you used an irrational number? The kind of number that can't be expressed as a whole number ratio. What if you used the most irrational number? Is there even such a thing as the most irrational number? Yes, there is. It is called phi. This is the golden ratio of the turn. And what's lovely about it is, you can see spokes, but you can see them going in both directions. They're kind of crossing over both ways. And you can try and count them, and if you do, you get Fibonacci numbers. Let's draw to verify whether it works for leaves too. You put your first leaf somewhere and the second leaf at an angle which is 1/5th of a circle. Great, your second leaf is pretty far from the first, gets lots of space in the sun. And now let's add the next 1/5th of the circle away. And again. And again. You can see how new leaves tend to pop up in the spaces left between old leaves, but it never quite fills things evenly. so there's always room for one more leaf without having to do a whole new layer. It's very practical and is a plant you probably like this. The Fibonacci numbers also occur in the sums of shallow diagonals in Pascal's triangle. It's not the numbers they show, it's how they grow. This pattern is not just useful, not just beautiful, it's inevitable. This is why science and mathematics are so much fun. You discover things that seem impossible to be true and then get to figure out why it's impossible for them not to be. To get this far in our understanding of these things, it took the combined effort of mathematicians, physicists, botanists, and biochemists.